Welcome to NPTEL lesson on a basic course on electric and magnetic circuits. In this lecture, we will discuss on how to obtain equivalent circuit of a magnetic arrangement, then followed by the required theory, how to solve magnetic circuits, and then you will discuss few examples on magnetic circuit. So, in last lesson we learned about the relation between phi, flux density B, H and the MMF. So, for a given magnetic circuit, like here a toroid is shown in this diagram, we know that from the Ampere's law H equals to N I upon L, MMF equals to N I, and length of the mean length of the core happens to be I L. Now, B equals to mu H Weber per meter square or Tesla, that relation also we know. We know phi equals to B into A, where A is the cross sectional area of the core. So, this is the iron core here on which the winding is, the coil is wound. B happens to be this average flux density, H happens to be this average magnetic strength of the in the core. So, now from this above three relations we can say the flux phi equals to B into A, but B equals to mu into H and H equals to N I upon L. So, substituting that we got phi equals to mu n I A upon L, and manipulating that we got the N I upon L upon mu A. So, this becomes equals to N I upon S, where S equals to L upon mu A, and this is called the reluctance of the magnetic path, where magnetic path is the path established by the flux phi in the core. The S has the unit of ampere turn per Weber, and this is followed from the N I happens to be this MMF F and the S reluctance. So, flux phi in Weber and N I ampere turn. So, this results in S to be equals to ampere turn per Weber. This is also mentioned as 1 upon P, S equals to 1 upon P, where P equals the permeance of the magnetic path. So, from this relation of phi, B and H, we obtain the flux in the core happens to be equals to the magnetomotive force supplied by the coil MMF N I upon the reluctance of the magnetic core. In conclusion, the flux which will be established in this core depends upon the MMF supplied, that is N into I, upon the reluctance of the core, where the reluctance of the core is L upon mu A. Mu is the permeability of the core, that equals to mu naught into mu r. A is the cross section of the core, and L is the length of the mean path of the flux. So, from this relation we say that the equivalent circuit diagram, magnetic equivalent circuit diagram, that becomes equals to F, we designate like this, plus minus like in electric circuit, and then we have the reluctance S, and then the corresponding flux to this path phi in this direction from positive to negative terminal. So, once again, when the equivalent circuit diagram of the magnetic path given this one is obtained, we obtain from the start from the source. Source is here the coil which provides N I amount of MMF So, this is MMF here, we start from there, and the core has a reluctance of S, and you connect the source to the reluctance, and then through this one a flux phi is being established. So, this is the corresponding flux phi in the core. So, for this magnetic circuit, the corresponding equivalent circuit becomes like this. So, this relation of flux equals to MMF upon reluctance is called the Hopkinson's law of magnetic circuits, and this is similar to Ohm's law that we say that I equals to V upon R, I equals to V upon R. Now, we can find an analogy between this magnetic circuit equivalent and the electric circuit. So, we say this is our magnetic circuit equivalent, MMF, reluctance, flux, similar to here the battery source with EMF E, resistance R of the load, and then the corresponding current flow becomes E upon R by Ohm's law, and this is governed by MMF upon S equals to phi Hopkinson's law. So, from these two equivalents we can say that the magnetic circuit, the MMF is equivalent to EMF, the source for that similar to voltage, and also voltage drop which you say encounter in the across the R, that equals to I into R. So, similarly, MMF equals to H into L also, because H equals to MMF upon L. So, that also will get. So, MMF here also H into L. So, that becomes equals to there also. So, that similar to voltage, the MMF happens to be there. Now, this MMF produces flux phi in the magnetic circuit, EMF produces current in the electric circuit, I equals to E upon R and phi equals to MMF F upon S. So, the corresponding current is limited by R equals to L upon sigma A, sigma is the conductivity, or rho L by A resistivity. Similarly, S the reluctance is L upon mu A, we have already derived. So, where mu is the permeability of the core material, that equals to mu naught into mu r, and mu r for steel happens to be 1000 and above in general, we have already seen in the last lesson. So, now we will see how for different magnetic circuits we can have different equivalent magnetic equivalent circuit, and then we will go for different problem solution. So, this is a case of rectangular core, and we have a coil here. So, this coil has n number of turns and current I flows through this coil. So, the MMF here becomes n into I. So, we start with MMF here, these are MMF. Now, with this MMF we start, and then we have a core. In the core, using the corresponding right hand rule, so the corresponding flux is established in this path like this, in this direction. So, flux here is like this, and the corresponding reluctance of this path is Sm. We have put it here, the corresponding reluctance of the path to be Sm, S for the reluctance, M for the magnetic path. So, the phi becomes equals to, in this case, as we have already discussed in the earlier slide, phi becomes equals to MMF upon S. So, this becomes equals to Ni upon, in this case, Sm. So, we can obtain like this, where the reluctance Sm in this case will be equals to L by mu A. L is the length of the mean core, this length, the path shown here this length, cross sectional area A, and then mu the permeability mu naught into mu r. This is for a homogeneous circuit, throughout this the corresponding material is of same. So, we call it as a homogeneous circuit. Next we go for the combination of a iron core, this is the core part and the gap part, air gap part. A cut is there in here. So, this is the gap part. So, this becomes a non-homogeneous case, a composite case. Now, you see here, once you energize this coil with a current DC current I having n number of turns. So, these are mmf Ni. So, we start with mmf Ni. So, depending upon the direction of the current, the flux will be established here. So, this is the direction of the flux. So, this flux passes through the core and also crosses the air gap. So, the flux in the core as well in the air gap in this case is same. So, that therefore, just like the current becomes same in different paths. So, it means that the different resistances are connected in series. Here also we say that there are two reluctances, S for the core part, this is SM1 for the core part SM1, and for this part SM2, gap part is SM2. So, this is SM2 and this is SM1 for the core part. So, the core and the air gap has two different S, and for the core the corresponding S core, that becomes equals to L core, length of the core divided by this mu of the core and the core cross section. Similarly, S for the gap, this becomes equals to length of the gap, air gap here, the small one, few mm or so, and then mu naught for air, mu r equals to 1, and then the corresponding gap cross sectional area. In this case, A g equals to A c, as you know. So, this leads to the situation that because for this composite circuit the flux happens to be same. So, we say that this is a series connected reluctance, series connection of the reluctance case. We will go to the next more complex combination of the magnetic path. So, here this is again a homogeneous series connected things. So, here you see the core, this core has uniform cross section up to this point, and here the core thickness is more. So, it put this part as SM1 and this part as SM2, these corresponding reluctances, because the reluctance depends the corresponding length and the cross sectional area, even though the mu happens to be same for the core. So, therefore, again the flux passes through, same flux passes goes from the source Ni. So, Ni here, and then flux here goes through this, crosses to the this path also same flux. So, therefore, this is also a series case like in electric circuit. So, therefore, we talk about here SM1 the major part of the core and SM2 the small part of the core where thickness is higher. So, this becomes a series case with a homogeneous series circuit case. The fourth case here again n into I, we have this mmf here. So, therefore, we start with this mmf I, and then this corresponding flux here goes here, and the flux is divided into here phi 1 and goes here as phi 2. So, there are two paths from here onwards for this corresponding flux phi, which is coming out of the source, that is the coil. So, therefore, this is a case of parallel case. So, phi 1 here and phi 2 here. So, for this phi 1 path we have SM1 and for the phi 2 path we have SM3 here. For the phi 1 part we have SM2 and for the phi 2 part we have SM3 here, and this part up to this point is nothing but the corresponding SM1 reluctance for the magnetic path 1, for the magnetic path 2 and magnetic path 3 from this point to this point. So, there are 3 paths here. So, these 3 paths are taken into account here. So, flux phi emanates from here. So, path 1 up to this point, this path is path 2 and the third part is this path. So, there are 3 paths and the corresponding reluctances are considered in the equivalent circuit diagram, and from there we can solve the corresponding equivalent circuit diagram. How to solve that we will analyze later. The fifth one also we can have more complex things in the central limb. In the central limb, so the corresponding mmf is being injected here. So, the source is here, this part, and then from here the flux goes, and the flux is divided here in terms of phi 1 and phi 2, phi 1 and the phi 2. So, therefore, this is one path and this is one path, this goes here phi 1 and this goes here phi 2. But what we say here that in this upper part we have an air gap here. So, therefore, this corresponding reluctance for the air gap becomes SM3 and therefore, the combination of core part and the air gap part. So, this becomes SM2 and SM3 two reluctances, and the lower part we have for the whole core, you can say that from this to this path. So, this constitute your SM4, the reluctance for the magnetic path 4, you can say that component here. So, this corresponding circuit becomes looks like this. So, these are the different combination of magnetic equivalent circuits. We can have more complex circuits having different combinations, like we dealt in case of the DC circuits or AC circuits, electric circuits. Now, we will go for the how to obtain the magnetic circuit solution. So, this is a circuit, an electromagnet with having an iron core, rectangular core here, and then we have an air gap here having length of Lg, and this part and having a core length of Lc. So, with this Ni here, so we got the equivalent circuit to be here, MMF to be here, and then the circuit here traces the flux goes through this core and also through the air gap. So, same flux. So, this is a series case. So, we have core part and we have the air gap part, two reluctances. So, this corresponding magnetic circuit equivalent becomes like this as shown here. So, reluctance of, as already mentioned, reluctance of the core equals to Lc upon mu c AC, length of the core in this arrangement, mean length. Then that of the gap is Sg equals to Lg upon mu g Ag, G stands for gap here. So, this Lg upon Ag mu g, in this case Ag happens to be equals to Ac. So, the common flux here phi equals to, the phi becomes equals to here MMF upon the reluctance. So, reluctance here S is the equivalent reluctance. So, this S becomes equals to Sc plus Sg, like we do in the series resistance combination case. So, this results in the corresponding Ni equals to, this results in terms of that we know Ni equals to phi into S from this, but we know also that the corresponding Ni equals to HL form. So, in this case we will having SCLC plus SGLG. So, that drop here plus the drop here. So, that is V into V equals to IR. So, that kind of form phi into S. So, phi into the corresponding S is nothing but SCLC and SGLG. So, this is your corresponding drop or MMF drop in the core part and MMF drop in the gap part. So, this is the combination in terms of that. So, we find the relations of two relations for the magnetic circuits in terms of MMF. So, MMF can be related and MMF equals to phi into S and MMF equals to also SCLC plus SGLG or summation of H into L, just like voltage drop case. From this also we say the how to find out the corresponding flux density. So, once you know the corresponding flux phi in this path, so flux density B c equals to phi c upon A c, and flux density in the gap becomes equals to B g equals to same flux phi g crossing the gap and the corresponding area cross section A g. There is a term called fringing. What happens that once you have this gap to be larger, then the tendency of the corresponding flux is bulges out. It crosses the corresponding gap and it takes path like this. So, the area of the cross section becomes more in this case. So, this is what this is what shown in clear in this diagram. Now, if the corresponding gap becomes more, so the corresponding bulging becomes more and more prominent. So, what happens by this way that the corresponding area of cross section here is not same as the what happens to be in the core area, it becomes larger. That means that due to this called the fringing, due to this the corresponding A g becomes greater than the corresponding A c what we discussed earlier. However, in general the corresponding gap is very small and in most of the cases the effect of fringing is neglected, and if it is neglected then we say that A g equals to A c. The air gap area through which the flux passes is same as that of the core area in general unless the gap is larger and fringing is accounted. There is another terminology we call useful flux and leakage flux. So, what you say that this is a DC machine case. So, from north pole the corresponding flux emanates and goes to the south pole and traverses a path to the stator like this. So, in this way the rotor, which is the inner circle, in this case the inner circle. So, the rotor, the corresponding flux passes through here one air gap, another one air gap. So, there are two air gaps which crosses the corresponding flux crosses to the in the magnetic path. So, it encounters two air gaps to its path. What we observe that in case of magnetic circuits like this. So, if the coil is concentrated here, so some of the flux does not go through this one, it traverses a path like this, and thereby this flux is not confined to the core, but in terms of the usage, the core flux is the usage where the flux is being used in the air gap in general at this portion. So, because it does not go to the through the core and through the air gap, so this became like wastage flux and called the leakage flux terminology. So, we see from that the flux which is crosses the rotor here and flux which crosses the corresponding air gap here are the useful flux, which is being beneficial for the particular applications, but the flux which it does not traverse to this core or the air gap is called the leakage flux. So, leakage coefficient lambda is defined the total flux divided by useful flux. In general, for systems the total flux is greater than useful flux. In an ideal case it becomes 1, the flux produced becomes equals to flux traversing through the air gap or the core. In machines in general, this lambda value remains to be 1.15 to 1.25. However, otherwise if the leakage flux in most of the cases in our simple calculations we assume to be negligible, in that case lambda becomes equals to 1. Let us take an example in our case now. So, in this case we have an iron ring with a circular cross section, and then we have a current I flowing through this coil uniformly wound across this, and it has an n number of turns. So, in the core a flux will be established and then related S, and the core length has an L. So, the data given here, an iron ring of cross sectional area 6 centimeter square, that is A equals to 6 centimeter square, is wound with a coil of 100 turns. So, n equals to 100. Relative permeability mu r is 470. Mean length of the core is L equals to 30 centimeter, L equals to 30 centimeter, that of the core, and the flux to be established in the core is 0.1, flux phi equals to 0.1 milliweber. Find the current required in the coil. Find the current required in the coil. So, what will happen once we inject a current I into these systems? So, then N I becomes your MMF. So, what relations we have studied? So, this MMF equals to MMF, and this says it will establish once and flux phi is there. So, flux phi into S, S is the reluctance of the path, where S equals to L upon mu A in this case. So, this becomes equal to MMF. Further, the MMF equals to, because flux phi also gives us H. So, this becomes equals to H into L. So, here everything is core, there is no gap. So, the corresponding relation becomes like this for this case. So, if we know that the corresponding flux phi is given to us. So, for this case, if we can find out the S, we can find out phi S, and we can find out this N I, and N is given. So, we can find out I. That is another one way of you can see that method. There is another method that from the flux phi you can find out this B phi by A, and from B you can find out this H So, once you find out the H, L is given to us. So, H into L is nothing but your N into I. So, therefore, we can find out the corresponding N. We know N equals to 100 in this case, we can find out I. So, in this example, because A is given in centimeter square, so we have to convert this to meter. So, 6 into 10 to the power minus 4 meter square, and then your L is 30 centimeter. So, this becomes equal to 0.3 meter. So, then this in milliweber. So, this becomes equals to 0.1 into 10 to the power minus 3 Weber. So, with this data input, we can apply two methods here. So, first method is about that HL equals to NI approach, and the second approach can be MMF equals to phi into S approach. So, in the first approach we will find out H, and the second approach we will find out S and proceed for, and that will lead to the same conclusion of the current in the required current for to establish the flux 0.1 milliampere in the core. So, the equivalent circuit for this circuit becomes equals to the NI, the MMF that we have already seen. So, this is positive negative. So, the corresponding flux will be established here, and then we have this S. So, this is your equivalent circuit for the magnetic circuit shown in this case. Now, in the method 1, as I said, so B equals to phi upon A. So, phi is 0.1 milliweber upon A is 6 into 10 to the power minus 4 meter square. So, we got phi to be 0.167 Weber per meter square. We know mu r. So, H equals to B upon mu equals to mu naught into mu r. So, 0.167 upon 4 pi 10 to the power minus 7, that is mu naught into 470 mu r. So, that gives us the corresponding H to be 282.78 ampere turn per meter. But MMF equals to Ni equals to H into L, length of the core is given to us 30 centimeter 0.3 meter. So, H into 0.3, that gives you 84.83 ampere turn for the MMF. So, this equals to Ni. So, this divided by the number of turns 100, this gives us the current required to be 0.848 ampere. So, this is method 1. Second method is based on this equivalent circuit diagram. So, this is we know phi into S equals to Ni. So, we will find the S equals to L upon mu A. L is 0.3 meter, and then mu is 4 pi into 10 to the minus 7, and mu r equals to 470. So, this is mu, and then A is 6 into 10 to the minus 4 meter square. So, this gives us the corresponding S becomes equals to 8.47 into 10 to the power 5 ampere turn per Weber, very large value. So, this Ni equals to phi S. So, this becomes phi into S, phi is 0.1 milliweber. So, this part, and then the corresponding S we multiply with this gives the corresponding Ni. So, Ni upon the corresponding number of turns 100, this gives us the corresponding I to be 0.848 ampere. So, by both the methods we find the corresponding current which is required for the coil to establish a flux 0.1 milliweber in the core of the arrangement. Now, we will see both the methods. So, we got the corresponding currents to be like this. Now, we will extend the problem to little bit more complex. So, what happened in this case, second case, is that in the earlier example with 2 millimeter of air gap. So, now we have an air gap of 2 millimeter in the circuit without the iron length change. So, the iron length path is not changed, only you have introduced a 2 millimeter of air gap in the system. What will be the corresponding current required to establish the same flux 0.1 milliampere flux in the core. So, the corresponding flux in this core which will be traversing this path from the for the core path and also cross the corresponding air gap will be 0.1 milliampere. To maintain the 0.1 milliampere, what will be the corresponding current? We have to find out. So, again we will apply the two methods. So, method 1 is for using the HL formula, Ni equals to HL formula. So, in this case what will happen, we see we will find the equivalent circuit diagram first, and then we can analyze it better way. So, you see here the corresponding equivalent circuit diagram first, this will be the corresponding source Ni, this is Ni, and then because it encounters the corresponding air gap and flux is same in the air gap. So, there are two reluctances in this case, series connected case. So, with flux phi. So, we say here S c the core and S g the air gap. So, for the S c this becomes equals to L c upon mu and the corresponding A c, and for the S g L c upon mu naught A g equals to A c in this case, A g equals to A c in this case. So, this is the corresponding path. So, one solution is N I equals to phi into S, where S equals to S c into S g, the other one H into L, the corresponding drop here and drop here. So, what are the drop? The drop becomes equals to S c into L c plus S g into L g. So, these are the two drops equivalent to the MMF. So, the MMF required for this part, core part, and the MMF required for this part is nothing but the MMF supplied by the coil. So, we will see how we go for this. The equivalent circuit diagram becomes like this, as I said. Earlier it was only one S, now it becomes two different S for the core part and the gap part. So, method 1, that is HL formula. So, we know now already we have found out the corresponding drop for this, because we say the corresponding flux in this core is 0.1 milliampere, flux phi is same, B same. So, B equals to mu H, mu same, mu already taken. So, H also same. So, then H and L c also same. So, the MMF drop here for the core also remains to same. So, we do not need to calculate. MMF for the core we have already calculated, and that is for the core is 84.83 we have already seen. Now, what we see that for the gap part we will calculate H g for the gap part is flux B is same, because phi by A is same, A g equals to A c. So, H g equals to B upon mu naught, mu r equals to 1 for the air gap. So, this B is already calculated in the earlier example 0.167. So, upon mu naught equals to 4 pi into 10 to the minus 7. So, this gives up the corresponding H g equals to 132.9 into 10 to the minus 7 ampere turn per meter. MMF for this AR H into H g into this. So, this gives us this and the multiplication of this. So, this gives up the corresponding things to be 265.8 ampere turn. So, the total MMF required is MMF by the core, that we have already calculated in earlier example. It remains to be same because flux is same, and the MMF of the air. So, total becomes equals to 350.63 ampere turn. The current I becomes equals to MMF by N, like we calculated earlier, that becomes equals to 3.506 ampere in this case. As discussed in the earlier slide on this magnetic circuit. So, we have H g equals to B upon mu naught. So, 0.167 upon 4 pi into 10 to the minus 7 for the gap part. So, that gives us 132.9 10 to the 3 ampere turn per meter for H g. So, therefore, this MMF for the air, that becomes equals to H g into L g, and that gives us the corresponding value L g and the H g, that gives us the corresponding ampere turn to be 265.8 ampere turn. So, the total MMF now for the core part and the corresponding air gap part. So, that becomes equals to 350.63 ampere turn. So, we see here that the ampere turn required for the air gap is much higher than that of the core. So, small gap 2 mmf gap, still the corresponding ampere turn is significant, because the mu r value of the core reduces the corresponding reluctance. So, once we get the corresponding MMF, so the MMF upon I, MMF upon N is nothing but our current I required in the coil. So, that gives us 350.6 upon 100. So, 3.5 ampere current is required to establish the corresponding flux in the core. If you go to the method 2 with the reluctance based approach, S into phi, N I equals to S into phi, phi is same, S is S g plus S core in this case. So, S core we have already found out. So, S g in this case is L g upon mu g A g, and this becomes equals to L g and mu g substituting the value of L g equals to 2 mm gap, and so we got the corresponding value to be 26.53 10 to the power 5 ampere turn per Weber. Note that the S g for the gap part is much larger because mu r is equals to 1, whereas the S for the core part we have already found out that becomes equals to 8.47 into 10 to the power 5 ampere turn per Weber. In earlier example we have already calculated. So, the total S for this part in this case becomes equals to S plus S g, and the total ampere turn required becomes equals to phi into S t. Phi is 0.1 milliweber. So, multiplying the S t you can say that we got this to be 350.6 ampere turn. So, the I becomes equals to mmf upon n, and that gives us again 3.506 ampere current required when we introduce a 2 mm of air gap in the earlier example. So, what we say that as compared to the earlier case of same flux 0.1 milliweber in the core, and the subsequent case same flux 0.1 milliweber in the core or the air gap, with the introduction of the air gap the corresponding current requirement becomes 3.506 ampere as compared to 0.848 ampere in this case. So, this is 0.848 ampere versus 3.506 ampere. So, we clearly see that the current requirement becomes significantly high with the introduction of the air gap, and the reason behind this is from the HL turn perspective. The HL drop here is significantly high compared to the HL drop in the core part. In the other perspective, phi into S perspective, S of this air gap part is much higher. So, the drop here also much higher. So, that is a series combination of 2 S, S core and S gap, and that leads to the requirement of more mmf to be provided from the source, and therefore, the corresponding current has to be increased because the number of turns remains to be 100 in both the cases. So, in general from this lecture we know how to obtain the magnetic circuits equivalent for a given magnetic arrangement, and then from this equivalent magnetic circuit analogous to electric circuit we know that the relation between mmf that equals to Ni equals to H into L, or mmf equals to phi into S. This is similar to E equals to V equals to I r, or E equals to I r, or I equals to V upon R. So, with the help of this electrical equivalent circuit similar to that we can solve the different magnetic flux related problem for a magnetic circuit. We will continue further few more problems on this in the next lecture. Thank you.